Hi everyone. Let's go ahead and start. Dean's just ordering more coffee. He'll be in a minute. Let me introduce our speaker, Dr. Luke Barnes. Got his bachelor's in physics from the University of Sydney and a PhD in astronomy from Cambridge University, and he's now doing a postdoc at the Swiss Federal Institute of Technology in Zurich. When he came in through customs in Atlanta, the person asked him, "So why are you here in the U.S.?" And he said, "A conference." And the customs agent said, "Oh, what's the conference on?" And he said, "Astronomy." And the customs agent said, "So you are an astronomist?" And Luke said, "Yes, I am, sir." So let's welcome our astronomist.
Thank you very much. So I'm hoping that catches on, actually, because it's a good word. So far as I understand it, my role here today as the token scientist is to give you a crash course on modern cosmology, galaxy formation, star formation and evolution, planetary formation and stability, supernovae, particle, nuclear, atomic and nuclear and molecular physics, biochemistry and biogenesis in this and all possible universes. So we'll get started. I have 4 lectures. They roughly go like this. The first one is just going to be a brief user's guide to the laws of nature, what they are and what you can do with them, and what the universe actually does with them. Second is going to be that rather innocent looking question, what if? What if we changed the laws of nature? What if we messed around with the universe? What if we could do that? What would happen? The third one, this is the bit that gets squeezed out if I run out of time. But basically, there are a number of responses that people give. I've given talks on popular level talks on this before. So there are I think about 14 different common responses, first responses that people give. Some of them are in the scientific literature, some are in the little bit of the philosophy literature that I've read, and some of them are from the internet. So various levels of sophistication there. Finally, we'll head off into the multiverse, and things are going to get weird in the afternoon. So the only thing to do is to jump right in, okay? So to just ask, what are the basic stuff of the universe, and what are the fundamental forces? What does the basic stuff of the universe actually do to itself, to each other? So, the main point of this lecture that you're going to need to sort of grasp a hold of as we go into the details is that a lot of the general features of the universe are not accidents, they're not sort of evolutionary adaptations, they're not just the subjective ways that we put the universe into neat little boxes. They are actually right there in the laws of nature. So in about half an hour's time, I'm going to be able to put an equation on the screen and say the rather memorable sentence, and there, in terms of the fundamental constants of nature, is a rather accurate equation for the height of a giraffe. So that is coming up in about 40 minutes, okay? So, let's start at the bottom, the very bottom so far as we know. These are the fundamental particles of nature. This is the standard model of particle physics. Let me take you through them. In purple, although they aren't actually purple, are the quarks. What you've got to think of these particles for the moment as just sort of a point with some properties. So they will all have a mass in particle physics units. That's a mega electron volt if you're wondering, but the details like that aren't going to matter. So they all have a mass, they all have a certain charge, they have a certain spin, which I'm not going to go into. We also see that they come in 3 generations and kind of 2 types. So these guys are roughly the same sort of mass, and then you get a step up in mass to this generation, and then a step again to the other one. So the up and down quarks, these names mean nothing. Okay, we had to call it something. We picked these for who knows what reasons. Okay, these ones all have the same charge as do these 3, and so we have 3 generations. Skipping ahead, it's the up and down quark that will make the proton, and you are mostly protons and neutrons. Okay, they are the quarks. We also have leptons. I think the name means something like light, something. Anyway, so the one that you will recognize, hopefully, is the electron, which, if you remember the model of the atom, the thing going around the outside, that's an electron. The electron has two older brothers, which are simply heavier but have the same properties, the muon and the tau. Named because that's a mu and that's a tau. The other ones are, we also have the electrons, again, 3 generations. There's a nice sort of symmetry in this table that is there, but we're not entirely sure why. You notice we think they have mass, but we're not sure what that mass is. And they all have 0 charge. They have electrons. Finally, we have the bosons. These are the force-carrying particles. So the way that when you teach an undergraduate sort of particle physics, the way you think of, say, an up and a down quark attracting each other, say, electromagnetically, is you say, well, the electromagnetic force is associated with the photon, which is itself chargeless, but these two particles then exchange photons. So if you think sort of two people at an ice rink throwing a ball to each other to repel each other, and I suppose if they threw magnets or something they might come closer, although the analogy starts breaking down there. So you have the photon. The photon is light particles. All you have ever seen in your life is photons, right? They're things hitting your eye, that's photons. There are also gluons. That name is exactly as dumb as it sounds. It's because they glue the particles together. Yeah, okay. We also have the particles for the weak force, which I just called the Z and W plus and W minus particles. So that. Oh, also for all of these particles, there is a corresponding antiparticle, which has exactly the same properties except for the charge. So, for example, the photon, which is chargeless, is its own antiparticle. Okay. Now, this might look like an awful lot of particles. I mean, there are 16, but there's actually 2 there, the plus and the minus, 17 particles, plus all the antiparticles. Actually, when particle physicists first really started firing up particle accelerators, a whole boatload of particles came out. Every week someone found something new. So that in terms of the next level up in particles, it's actually a lot worse. Okay, I'm not going to go through this in detail. Again, we see dumb names all over the place. We don't know what to call these things. So that, I mean, it's a sigma particle, that's a delta particle. We just go through the Greek alphabet, basically. The point is that this is an advance on that. All of these can be made out of, actually these ones are all from the quarks. So that's the basic stuff of the universe. Next we need to know what are the forces. Now I've mentioned the forces because the bosons are the force carriers, but there are 4 fundamental forces of nature. Perhaps the most familiar is gravity, which we are all familiar with. Anything with all forms of energy find other forms of energy attractive. So our most advanced theory of gravity is Einstein's general relativity. We don't have a quantum theory of gravity yet, but smart people are working on it, so stay tuned. In special cases, it will reduce to.
Do you want to take questions in the middle?
Yeah, I should say I'm here all week, so quick questions are fine. But if it's anything too long, I'll just say, yeah.
You pointed to the sigma particles and said they're made up of quarks.
Yes.
Made up of, do you mean the quarks are parts of them, or something else?
Yes, but yeah, just think of three quarks being stuck together with gluons, and that it's exactly as dumb as it sounds. Yes, yeah. Okay, gravity. Electromagnetism is also very, very familiar. Ordinary contact forces, that's electromagnetism. The electrons going around in an atom will feel the other electrons and be repelled by them when they get close. So, what else to say? So, also magnetic forces are also obviously a part of electromagnetism, and light itself is an electromagnetic wave. And I've just told you that the photon is a particle. So if you've heard anything about quantum mechanics, you know those two statements go together, and I'm not going to explain them any further. The strong force. The strong nuclear force is between quarks. It's what holds quarks together. It's the thing about the strong force, it has a limited range. So that if you think of, say, you can think of the strong force as being like a very strong, muscly arm. So when you're in its grasp, it's really got you. But if you're just out of reach, it doesn't hold on. So the strength of the force drops off very quickly. Finally, the weak nuclear force is a type of interaction. The importance for later on is it's the only type of it's the only type of interaction whereby you can change a quark into a lepton and vice versa. That will be important later on, so I'll skip over it for a moment. I put there 4 constants: alpha G, alpha W, and alpha S. That give us the strength of these forces. They are dimensionless numbers, and basically the bigger the number, the stronger the force. So the strong force is the strongest. So alpha S is about 0.2. The next strongest one is electromagnetism. Alpha, which is the prototype for all of these, it's called the fine structure constant. It is about 0.007. So it's 1 over 137, famously. Well, famously. The weak nuclear force, that number is about 10 to the minus 6. Oh, are we all okay with scientific notation? Yes? Okay, let me say it this way. Is anyone not okay with scientific notation? Needs me to run through it on the... Good? Good. There'll be a test later. 10 to the minus 6, and finally gravity is significantly weaker than all of the other ones. The coupling constant there is about 10 to the minus 39. Now, a quick point. These 3 are actually all functions of energy. It depends what energy scale you're considering. The ones I've given, the numbers I just gave you are for energy sort of relevant to atoms and nuclei. So more on that in a minute. Now, there are 2 other sort of conceptual forces I want to give you. These aren't so much fundamental forces, but it will help to keep them as a separate category for later on. So they are the 2 on the top there, the degeneracy force and thermal pressure. Now, both of these, just sort of the thermal pressure in this room is really down to electromagnetism, but it'll help to keep it, if we keep that sort of separate idea. The idea of thermal pressure is very simple. Think about a box of just, those super balls, really bouncy balls. So if you had a box of those all bouncing around with each other, they would bounce off the walls and off each other, and they would exert a pressure on the wall. So if that wall was very weak, they'd break right through it. So that is thermal pressure is just the combined pressure, thinking of all the atoms in this room as a gas bouncing off the wall. Degeneracy pressure takes us into the sort of strange world of quantum mechanics. If you have a bound system, then what that means is the energy in the system isn't enough for the system to pull itself apart as far as it would like. So a system that will always stay within a certain distance of it's always going to be contained. What quantum mechanics tells us is that bound systems are quantized. What that means is of the ways that you can configure the system, there are discrete places, there are discrete configurations the system can have and cannot have. So, for example, planetary orbits, this is not a quantum mechanical system because quantum mechanical system is very small. But if you had, you've got your star there and you have a planet in one hand, you're very strong, you can put that planet in whatever orbit you like. I would like the planet to orbit this far away, and you have to do a calculation to see how hard you need to throw it to make it go back around in a circle. But you can do it whatever you like. Whereas in a quantum mechanical system, say an atom, so you can think of now I'm holding a nucleus in one hand, I have an electron which I'm going to make orbit around. You can't put it wherever you like. Okay, there are certain states. It could orbit here or here, but not in between. Okay, what that means is this is what's called the Pauli exclusion principle. Well, what it says is that you have a set of states. You have a set of places that the electron could orbit and nowhere else. And if you have what are called fermions, so electrons are an example of fermions, you get one electron per state, and you can't put another one in there. Okay? What that means is the system is going to fight you if you try to squash it. Okay? Now, in the case of the thermal pressure, I mean, it is fight. If you try and push this wall in, these particles will hit the wall more often, and so it will fight you. Okay, think about a balloon and just trying to squash a balloon. It's fighting you. With degeneracy pressure, it's even worse because you're trying to squish things into smaller and smaller orbits, but you can only get one per orbit. So if you keep trying to squish it, you have to put in more energy to put it in a higher orbit. This is kind of hard to explain without the maths. Basically, the system is fighting you, and it's fighting you even better than thermal pressure. Okay? We'll talk more about the degeneracy force later. It's actually a quite important force in the universe. Okay? Very quickly before I move on, units. It's a good idea at the start to pick a system of units. So for example, you choose the length of, you choose your length scale that you are going to define as 1. So if you have meters, which is, you should, you define the meter, and that's 1 meter, and then every other distance you compare to the meter. That's 5 meters, that's half a meter. Okay? You can choose whatever system you like. I mean, there are smart choices and less smart choices. We pick ones that are sort of nice and human-sized. But you can pick, the same applies to time, the same applies to mass, and also to temperature. A good unit is, these are 4 fundamental constants of nature. G is the gravitational constant, C is the speed of light, h bar is a constant from quantum mechanics, which if h bar was 0, then the quantum mechanical forces would be non-existent. If it was large, then the quantum mechanical effects would be larger. And Kb is called Boltzmann's constant. It's a good idea if we pick our units so that all of these have the value 1. And we can do that if you pick what are called Planck units. Now, these aren't used in everyday life because they'd be very, they wouldn't be very useful. For example, the Planck length is about 10 to the minus 35 meters, something like that. And so, how far away is the back wall? It'd be an awful lot of Planck lengths. What this does, I mean, later on we're going to change the laws of nature. If you set your units now, you won't end up just making a scale model of the universe. If you start changing things, you really will change things. You won't just make a scale model where it's all actually the same, just a bit bigger on some arbitrary scale. All right. What we're going to do now is we have the fundamental things, the stuff of nature, and the fundamental particles. The fundamental particles, fundamental forces. What we now want to do is to say, what can we make with them that will not fall apart as soon as we have made it? So what we are looking for is equilibria, but more than equilibria, we want stable equilibria. So this is the classic diagram of that. Both of these points are equilibria. If you put that ball exactly there on that hill, it will not move. If you put that ball exactly there on that hill, it will not move either. They are different in terms of their stability. So what you think of doing is you poke the system and see if things only get worse or whether they tend to cancel out. If I poke that ball a little bit, it will come back to where the equilibrium is. If I poke that ball a little bit, that little poke, no matter how small, is going to get amplified and going to get worse. Okay? So we will be looking for equilibrium where I can take the laws of nature and I can make something and it'll be nice and stable, so if it gets poked by a passing atom or something, it won't just fall apart into nothing. So we don't want sort of perfectly poised, unstable equilibria. So let's get started. Composite particles. We can make things out of quarks, like the delta particle. Okay, I've sort of said that already. Gluons will hold them together. There are various rules for what are allowed, but what we're interested in is the stable ones. Now, that's quite important because if you make a particle with a large mass, remember Einstein's E equals mc squared? So mass is a form of energy. So a particle with a large mass has enough energy to make smaller particles. And actually, it will decay into smaller particles with a certain lifetime. What that means is, of all that ridiculous table that I showed you of particles, there are very few which are actually stable. This is why particle physics is so hard, because you have a very short time to actually spot the particle before it turns into something you've already seen. So in actual fact, all of those particles boil down to these four. The electron we've already met, the neutrino we have already met, the neutron, which is an up and two downs, and the proton, which is two ups and a down. And that's it. All the rest are unstable. So this is quite a simplification. Actually, technically, the neutron is unstable if it's out on its own in free space, but if you put it inside an atom, inside a nucleus, it will be stable. So you're about half neutrons, roughly. Even these four, the neutrino only acts via the weak force. It's uncharged, and it's a lepton, so it doesn't feel the strong force. And so the sun, for example, produces neutrinos at a tremendous rate. There are trillions passing through this room, and they are just passing through this room. They go straight through the Earth and out the other side. If you want to detect a neutrino, you have to do something like you get a... They interact so often. You go in a very deep mine shaft, and you basically fill the biggest hole you can find with a kind of detergent liquid. It's a dry cleaning liquid. It's the easiest way to get it in huge quantities. And when the neutrino hits something, it'll make a change. So you leave it there for ages, and then afterwards you analyze this whole huge lake of detergent that you found and see if there's anything changed. So yeah, that's not the kind of physics I do, thank goodness. Okay. Next, nuclei. Yeah.
Quick question. When you say these are stable, do you mean absolutely stable or do you mean very stable?
I mean very stable. There is a theory that the proton is unstable. It's fairly robustly predicted, but never actually been observed. Okay, nuclei. We can put protons and neutrons together to make nuclei. Okay, so we might be starting to wander in something that you remember from chemistry in high school. I'm hoping. Okay, so the strong nuclear force will hold these together. Now, this is sort of the picture that we have. So you have neutrons, which are red in the diagram, protons, which are blue, and they're all together in a great big lump, and they're all holding themselves together. Now, can we make any old collection of protons and can you just order any, I'll have 20 protons and 1,000 neutrons, thanks very much. No, there are two forms of stability. Well, remember the protons, remember the tiny muscly arms, okay? This guy is only really holding on to its nearest neighbors, okay? But, remember these are positively charged, and like charges repel. So at the same time it's being repelled by not just its nearest neighbors, but the whole thing. If you make it too big, the repulsion starts to win, okay? The tiny muscly arms, they're very strong, but if you make it big enough, there'll be enough repulsion there to make the nucleus fall apart. Okay? Now, you can counter this by adding neutrons. The advantage of neutrons is you add more tiny muscly arms without adding more charge, so it's not unstable. The problem then is, remember the neutron is unstable. If you leave it isolated with only neutrons around, it will decay, is a good way of thinking about these things. So if you have a nucleus with too many neutrons, that also will be unstable, remember? Stability is what we're after here. What that means is, of all the ways, so you can think of, you order, I want this many protons, so I want 60 protons, and I'd like 90 neutrons, please. And so you go up on this diagram and you go, okay, 60, 90, okay, sweet, that one's actually stable, that's a black one, okay? Slightly off to the side, the unfilled circles are unstable eventually, they will decay, although something like uranium-238 has a half-life of a couple of billion years. So unstable, but it depends, how long you can, how long you need it to hang around for. This is called the valley of stability. So all these out here and all those out there are completely unstable. They haven't even been made, let alone, held around for a while. So that's nuclei. What we'll now do is we'll stick some electrons around them and make some atoms, okay? Now, the important thing here is you might think, okay, I've got a positively charged nucleus, I've got an electron, which is negatively charged, they'll attract each other. If I put this in the right orbit around, it'll be like the Earth going around the sun, and that'll be great, that'll be stable. Actually, classically, this won't work. There is a theorem in classical electromagnetism called Earnshaw's theorem, which basically says it can't work. A collection of charges cannot be stable using only electrostatic charges. So you can't actually make something stable with just classical electromagnetism. This was a massive problem in physics about 110 years ago. Is that the best thing we knew about, we only had classical electromagnetism. We knew that there were charges, positive and negative charges in the atom, and we knew that that can't possibly be stable. The lifetime is 10 to the minus 13 seconds. How do atoms last? Quantum mechanics saves the day via this degeneracy force. So remember I said that bound systems are quantized. The most important point there is that these are the levels. Remember I said there are certain levels. This is for a hydrogen atom. The details don't matter. These colored lines don't matter. The point is that if you have an electron, it can be here or it can be there, but it can't be anywhere in between. And the very important point of this plot is that there is nothing below there. Okay, that is the ground state. Yeah, sorry, there's a line there. It's not much to see. There is nothing below the ground state. So if you put an electron in this state, it will undergo, it will emit a photon and drop down through the states, but it will not just drop down into the nucleus because there is a ground state. There is a bottom floor below which you cannot go. Now, we can understand this in terms of the uncertainty principle of quantum mechanics. Now, I don't know how math phobic everyone is, but we're going to go through an equation. It's going to be okay. This is the famous uncertainty principle of quantum mechanics. What it says, what quantum mechanics gives you is a set of states. And the idea is, if I specify a state, what that is it's everything that I can know about a system. Okay? You think of it as a black box, and I can ask this black box questions. The point of quantum mechanics is, if you ask it a question like, where is the electron, you will not get the same answer every time. There is an uncertainty in the position of the electron. If you ask it what is the momentum of the electron, basically what is the velocity, the speed of the electron, you will not get the same answer every time. You'll get a range of answers. The uncertainty principle says that the range you get for position multiplied by the range you get for momentum has to be greater than, there's h bar, which I said before, this number. Now, in ordinary in ordinary units, in ordinary European units, that number is about 10 to the minus 34. Okay, which is why on a macroscopic level, quantum mechanics just does not matter. So you do not need to worry about the quantum mechanical uncertainty of where the coffee is when you need to go get a coffee. If you spill the coffee, it's all you. Okay. You can now think, okay, if I tried, if an electron was to fall into a nucleus and stay there, I would have confined it to a very small place, and it's staying there, so I must have confined it to a very small momentum range as well, which is not allowed, okay? So it's quantum mechanics to the rescue. Now, you can actually do the calculation for how big an atom is then. How far from the nucleus will the electron go? I was going to derive this. I've decided not to. I can do it for anyone, we can spend a few sheets of paper working on it. The point is that this number is all the constants of nature. That is the mass of an electron, and that is, you remember alpha, the fine structure constant. Okay? So if alpha was bigger, electrons would be smaller. Atoms would be smaller. If the mass of the electron was higher, then electrons would be smaller. Okay? So that's sort of case one of what I've, go.
Oh, quick question. So the uncertainty, is that epistemic, meaning we don't know, we can never know, given our limitations,
That is the million-dollar question of quantum mechanics. And yeah, we don't know.
I was just going to comment, if alpha is smaller, it's only it only makes the atom smaller in Planck units, because if you use atomic units,
Yes.
it remains the same
Okay.
size.
Yeah.
So it really depends on the units you use.
So yeah, that's why I set my units at the start.
that's
So
for Planck
cool.
units.
Okay. The point is that this is just all the constants of nature. Remember what I said, the main features of our universe are all there, and the size of atoms is not an accident, it's not an evolution, it's not just some number we pulled out of nowhere. It's right there in the equations. Also, note the irony here. Whenever you hear someone talking about quantum mechanics, they're always talking about, determinism is lost, the universe is random and completely chaotic and pathetic. And all right, it's quantum mechanics that's holding your atoms up, right? The stability of every atom you see in this room is quantum mechanics, right? It's in the absence of quantum mechanics that we're in big trouble, right? They all fall apart in 10 to the minus 13 seconds. So that is a nice point of irony that I would like to point out. Okay. The electrons going around the nucleus, that is chemistry, especially the outer ones, okay? The way that if you bring two atoms close to each other, the electrons in the outer shell will interact with each other. That is chemistry. Chemistry simply is the study of valence electrons, although a chemist won't say that. Much more important. Okay. Now the reason why if you have a different nucleus, you have a different charge in the middle there, you get different chemical properties, is because, remember the exclusion principle. I have this orbit here, and actually this diagram isn't the best, but you can, if you think of this, the nucleus, the electron can spin this way, or it can spin the other way. So you can actually put 2 per orbit with 1 per spin state. The exclusion principle then says, okay, those 2 are full, but to make a neutral atom I've got 4 more to put in, so they have to fill up these higher orbits. These different orbits have different properties, and so the chemistry of all the different atoms in the periodic table is different. Have you all seen the periodic table before? Has anyone not seen the periodic table before? Okay? Good. They all have different chemical properties because in the end they all have electrons in different areas around them. Okay? They don't all just fill the ground state and all just hang out there and are all the same. So they're all very different. So carbon is very different from chlorine, etc. So I've already said this, but we can bind atoms together to make molecules. So here's water, which you've hopefully all seen before. So an electron orbiting around a hydrogen atom in its orbit then sort of takes off around an oxygen atom, and they bind themselves together. If hydrogen tries to take off and take its electron, the oxygen atom will try to hold on to that electron, which holds the whole thing together. Okay, so this is a very simple example of a molecule. It's actually a very amazing molecule for reasons I will tell you later. But I mean, chemistry can do rather extraordinary things. Okay, this, as I hope you all know, is DNA. This can carry information. Okay, that's a very important property in terms of life. Okay, that, you know, you can put the instructions for a human being into a molecule and then fit it in a tiny space. The next point is in terms of the constants of nature, we can calculate the typical energies that will be involved in any chemical reaction and the typical energies involved in any nuclear reaction. So for a chemical reaction, you're just messing with the electrons. For a nuclear reaction, you're in the nucleus messing with the protons and neutrons. Okay? That number, which depends on the strength of electromagnetism, because it's electromagnetism that's holding the electron on and the mass of the electron, and the strength of the strong force, which is holding the nucleus together, that number is 10 to the minus 5. Okay? That is why alchemy doesn't work. Okay? It's not banned, you're just never going to do it. Okay? If you try to light really hot fires so that you can turn lead into gold, you are going to come out 100,000, a factor of 100,000 short in energy, which is good, right? You don't want to start nuclear reactions when you're trying to just heat your house, okay? Nuclear reactions are hard to do. Thank goodness. Okay? This is why chemistry is just chemistry. You can just do chemistry and not have to worry really about the nucleus, okay? You can't burn your cake in your oven and end up with a pile of lead, okay? It's going to undergo chemical reactions, but there's no nuclear reactions there, okay? We're now going to move beyond. We've been looking at sort of single entities, but now we can put them together into different phases. There are more than 3 phases of matter, but these are the important ones. In a solid, these interatomic forces are all there, just sort of held together in a grid, which the whole grid might sort of rumble a bit, but nothing much moves. In a liquid, think about if you had a box of sort of smooth magnets. So, and then you shook the box. So at every time a magnet would be would want to line up sort of north to south. But if you shook the box hard enough, it would click between different the ends would just click around between each other. They'd jostle around. So at each point there's a molecular bond there, but they're constantly changing which one I'm bonding to as all the molecules jostle around. And in a gas, we're just completely free. So two air molecules come together. They would form a bond if they were held there, but they're going so fast they just bounce off each other. There's too much energy. There's enough energy there to break the bond even if it forms. We can actually then use the constants of nature to find what's commonly called a biological temperature, which is the average temperature at which solids will form liquids and or gases. And again, you see, this is all just in terms of the constants of nature. So this temperature is basically cooking temperature, right? If you want to cook some eggs, the temperature you need is right there in the constants of nature. Too little and you don't end up breaking bonds, any bonds. Too much and you've broken all the bonds, right? We're now going to take another step up in size. So how big can a rock be? Okay, we're thinking about solids. What's the next step up? What's the next bit of physics that comes in? The next thing, the thing we've ignored the whole way is in fact gravity. At some point, gravity is so big, if you increase the size of your rock, at some point its own gravity is so big that it will start reshaping the rock. The force on any bit that, if it's a perfect sphere, then all the force is, all the pushing force is all equal. But if a bit sticks out the side, there's more force on that bit, and it will try to make it push down. This is why mountains fall over if they're too high. If you've built a sandcastle, if you build it too high, eventually it gets crushed down. So again, we can calculate what this is. So if you're smaller than this limit, you're an asteroid, or just a rock. And you can be any sort of irregular shape. Bigger than this, and gravity will crush you into a sphere, like the one you're on right now. Okay? We can find out what the line is between these two cases. And once again, all that appears in the expression are the constants of nature. Okay? This is just a fudge factor to make things work better. It's a rough calculation, so we won't worry about things like that. The mass of the electron, the mass of the proton, the fine structure constant for gravity, and the mass of the proton again out the far side to make the units make sense. Okay? What's the smallest size of a planet? It's not an accident. It's not just, we just decide, we'll call that a planet. It's right there in the laws of nature. Okay? If you're bigger than this, you must be round. Okay? Now, that number is going to be pretty big, and certainly, yes?
Just had a question, now that you've said it a few times, that it's not an accident, it's right there in the laws of nature.
Yeah.
And it seems like this is just an equation telling us what in fact is the case. And you might think it's just an accident that it's true in whatever sense that means. So can you give a little bit more context?
Well, I guess what I'm saying is it's not just it's not just an accident of the initial conditions, I think is what I'm trying to say. It's not just how our universe happened to turn out. The second half of this talk is going to be entirely about the initial conditions, how our universe started off, and what it actually does. And I think that'll sort of bring the difference into a bit more, a bit clearer. What I was saying was that number is big and this number is small. They are the numbers that have the units of mass. So one of these numbers is going to have to be big if your planet is going to be a lot bigger than a proton, which we would like our planets to be a lot bigger than a proton, okay? That ratio there is about 1 on 1,000 to the power of 3/4 is still about 1 on 1,000. So that's not a particularly big number. Remember this, the mass of a proton is 10 to the minus 27 kilograms. The mass of Earth, wait for it, is 10 to the 24 kilograms. So what is that, about 50 orders of magnitude difference, 50 factors of 10 different, okay? So that one gives us 3, that's no good. Alpha was about 1 on 100, so that's no good either. It's the weakness of gravity. The fact that that number is so small, so 1 over it is so big, that means that planets are big. We'll see a lot more of that later. So what's next? Oh, yes. I'll just take you on a quick tour through the planets. Just to give you a break from my voice. Right. The second half of that is coming up later. What's next? So at some point, remember, a big part of what's sort of the next 10 or 15 minutes is what's fighting gravity. Keep asking yourself that question. Okay, gravity is always attractive, so it's always trying to crush whatever it's got a hold on. Okay, so we saw that if you've got a planet, then it's crushed it into a sphere. But what's fighting gravity is just intermolecular forces, the forces that are holding up the molecules. At some point, you become so big that if you keep making a bigger and bigger thing, that will fail as well. What happens next is that it will be degeneracy forces that hold the atom up. You're trying to squish all the particles together, and they don't like it. Okay? Again, that gives us a maximum size of a planet. If you're bigger than that number, then you're not what we would usually call a planet. Okay, you're not held up by just ordinary molecular atomic forces. You're what's called a brown dwarf. Okay, once again, very big number, very small number. So it's the weakness of gravity, the fact that that number is very small that does all the magic for you. Okay. Brown dwarfs aren't particularly interesting. What's really interesting is if you can make gravity be fought by thermal pressure, and then you've got a star. However, the problem is anything with a temperature will radiate electromagnetic waves. Okay, you're doing it now. Anything with a temperature will do it. So a star being particularly hot will do it, and it will cool off. So if you want a long-lived star, you need some source of energy. Now that source is actually the strong nuclear force. So stars, as you might know, are running off nuclear fusion. Okay? Again, at what point does a brown dwarf become a star? Keep piling it on, and you get this number. The point of these equations, is not to remind them, but that I don't have to know how the universe started to know what these are. If you gave a man in a cave just the equations of motion, the laws of nature, and a lot of paper and a lot of time, and he was quite clever, he could work all this out without actually knowing whether there are in fact stars in the universe. This is all just from the laws of nature. Okay? There's a particularly familiar star to all of us. Why are stars stable? Now, the reason why they're stable is you do what we said before, you give it a poke and see what happens. If the star happens to collapse a bit, it will heat up, the density will get higher, and so the nuclear reactions will fire up more. And so they will push the star back out. So if you push it in, it will fight you. If that overshoots and the star expands a bit, the nuclear reactions slow down and the force outwards decreases, so gravity can win a bit and it pushes you back to where you started with. So that's that stable equilibrium I was telling you about. If things aren't perfectly round, and they're not, if you get a slight perturbation on the system, it will restore itself. Okay? At some point, however, if you keep making stars bigger and bigger and bigger, there is a maximum you reach. The problem is that the pressure, which before was just thermal pressure of particles, now there are more and more photons inside the star. And if the main source of pressure for the star is photons, then for reasons I don't know how to explain without an equation, the star will be unstable. It will basically overcorrect. So if you push it in a bit, it won't just sort of nice and slowly push you back. It'll overshoot and blow mass off. So anything bigger than this, there should be sort of a constant out the front, but that's roughly right, will be unstable in that way. Now, all of these numbers, the stars in the universe all contain between about 10 to the 56 and 10 to the 59 protons. Now those are weird numbers, right? You wouldn't expect those off the top of your head. How on earth, 10 to the 56, 10 to the 59, but using just rough arguments like these, we can actually get a handle on where these numbers come from. So, once again, let me finish off this for you whilst I get a drink. You still see the sun? No? There it goes.
Is this true color?
Yeah, I think so. Roughly. And that's the end of that. So there is quite a range there, but we can get a handle on why stars are all in that range, and it's in the laws of nature. Okay?
Just a curiosity. So if it's all in the laws of nature, it's not arbitrary. What was the controversy with Pluto about?
Oh, that was just nomenclature.
So they could just look at that.
It was, what do we want to call a planet? Is it what we historically called a planet, or do we want to have some physical definition of it must clear its own path, it must be this, that, or the other? So exactly what a planet is. Yeah. Okay, very quickly, let's go through I've said that stars use nuclear reactions, but let's look quickly at what those nuclear reactions are. Basically, we start with 4 protons, and we end up with a helium nucleus. Okay? Now, if you're very sharp, I'm sure you are, we started with 4 protons, and we end up with 2 protons and 2 neutrons. Okay? What that tells you is, at some point hidden in this arrow is a weak interaction. Now, there's a crucial process in stars which involves the weak force, which means that it's unusually slow. Now, that doesn't mean that stars burn slower than they otherwise would. Okay? The rate at which stars will burn their fuel is determined by the macroscopic properties, by the stability, the overall stability of the star, not the sort of microscopic details. What it does mean is that stars have to be quite hot to get this reaction working. Now, this is obviously the simplified version. The more complex version goes like this. I won't take you through the details. Basically, all you need to know about this is we start off with protons, we then get deuterium, and the most common reaction then is we put helium-3 into helium-4. The moral of the story is that we have to make deuterium along the way. That's another story. Being a fine-tuning talk, at some point we will be talking about the triple alpha process. Once a star runs out of hydrogen, if it's big enough, it will continue to collapse, and if it's big enough and hot enough, it will eventually be able to start whacking 3 helium nuclei together via beryllium to make carbon. Now, in terms of life, that's obviously important, okay? You are made of these. So it's obviously important that stars can make them somehow. The lifetime of a star, I won't go into this very much, but again, if you want the lifetime of a star to be very long, again, it boils down to the fact that this is a small number, and so to the minus 3/2 is a big number. It's the weakness of gravity that means that stars have to be big if they're going to fight nuclear reactions, and if they're really big, they have lots of fuel. Let's go through very quickly we've made carbon inside of a star, but if you want carbon to be on, say, a planet and then in a person, you're going to have to get it out somehow. So we need to know what happens when stars reach the end of their lives. What happens is that we had hydrogen burning and it made helium. If it's big enough, helium will start to burn to make carbon. This all happens at the center of the star. So what you end up is sort of layers. Then carbon starts burning to oxygen, oxygen burns to neon, to magnesium, to silicon, and to iron, all the way down through the star. So you get this onion type structure. Okay, this cannot go on forever. Okay, because iron is as far as you can go. Okay, this is the number of nucleons in the nucleus, and this is average binding energy. What you need to know about this is you start off with helium, and hydrogen, we burn to helium. If you're going up, then you're getting energy out, which is good because you're trying to fight gravity. So we need to keep going up. Okay, helium, we burn to carbon, we keep going up. Carbon, oxygen, neon, we hit iron, and there's nowhere else to go. Once you've got a star where the core is made of iron, any nuclear reactions are going to take energy away from the star, which just makes things worse, right? You're trying to fight gravity. We need energy to fight gravity. So at this point, things get a bit catastrophic. Now, if you have a small star, the star will throw off its outer layers in what's called to become a planetary nebula. But if you have a very big star, it will go supernova. The star will basically blow up, which is actually quite useful because remember we made all those nice elements in the shell around the star. So if we can blow them off out into the universe, then they'll be there for planets. Okay, I've got 70 minutes. Yeah, we're good. Okay, what else can we make? That was stars. Obviously very important. We're going to be talking about fine-tuning. Stars are very important to life in the universe. Also important, planetary orbits. So if you have a planet in an orbit around a sun, that will actually be stable. So if you put it in a perfect circular orbit, it will come around to exactly where it started. If you slightly miss a circular orbit, then it will still come back to where it started. It'll just take a bit of an ellipse, sort of an oval shape. But you'll end up where you started. You won't spiral into the star. You won't take off out into the universe. So that's nice and stable. There is another form of stability. This is due to something called the virial theorem. If you had, this is a photograph of a star cluster. So you have a large number of stars. Each of these dots is a star. You have a large number of them all feeling each other's gravity, and so gravity is pulling them all together. Now, in this case, what's fighting gravity to keep this thing up is, in fact, kinetic energy. That when they get to the middle, they're moving so fast that they just shoot out the other side. The stars themselves are so small that there's a very, very small possibility that they will actually collide, which is unfortunate because that would be kind of cool, but it just doesn't happen. Okay, so what actually happens, okay, this is now a simulation. So that last one was a picture, this is a simulation. Oh, that's so terrible. That resolution is just awful. Okay, try and follow one of these stars Okay, the stars are taking an orbit. They sort of come pass through the center and just shoot out the other side. There's a characteristic size here. If it got too small, then everything would be moving really fast, and so they would go further out. And if it was too big, then gravity would win and make it slightly smaller.
Is this a set number of stars that are they coming back around? Or are they
Yes.
Okay.
Okay. Very rarely, very close two-body interaction. If two stars go very close to each other, one of them can be sort of swung right out of the system. But the time scale for, so eventually the system will probably be unstable.
What keeps them sort of coming back to that?
Gravity.
Cluster?
The combined gravity of all the other stars. Yep.
I don't know. I mean, are they making like very large orbits to come back around that spot?
Well, I mean, some of them are. Some of them are making small orbits around the center.
That spot rather than some other spot. Like in the solar system, you've got the sun in the middle.
Yeah.
The central mass bringing planets around.
Together they define a center of mass. Okay.
Right.
Yeah. 4 minutes. Let me very quickly show you some nice pictures of galaxies, because it's what I study. There are two types of galaxies. There are the nice ones that you've hopefully seen called spiral galaxies, which look great when you give a talk. There are also the boring ones called elliptical galaxies, which are roughly the same size. The galaxies are basically stable. These ones, you can think of their stability as if this was a great big solar system. So these guys around the outside are orbiting in roughly sort of circular orbits around the center. This guy, you can sort of think in terms of that star cluster. It's just a sort of really big star cluster. So these guys are stable because because not of the ordered rotational motion, but because of the random motion of all these stars sort of passing through each other. Can't resist to show you a few more nice pictures because they're very nice. Making galaxies, I won't do too much on this. We need to do a bit more of this in the next lecture. The important thing about gravity, you think about what's fighting gravity. In this case, it's thermal pressure. But to actually make a galaxy, we need thermal pressure to lose. Okay? In all the other cases, we needed thermal pressure to win, to hold it up. We actually need thermal pressure to lose. If thermal pressure can hold the sort of gas in a galaxy up, it won't really form a galaxy. It will just form a huge ball of hot, very diffuse gas, which is no good. You won't make stars, you won't make planets, you won't make anything like that. We need the gas pressure to lose so that so the whole thing collapses, and what eventually stabilizes it is rotational orbits when it's very small. Very roughly, you can do a sort of calculation to get a rough size of the mass of a galaxy by setting equal what's called the dynamical time, which is how fast gravity is changing the system, and the cooling time, which is how fast pressure is losing. So if you're bigger than this, pressure wins, and you just get a big hot ball of gas.
Can you say something basic about why galaxies are shaped different from solar systems?
I'm going to go through galaxy formation in the second half. I'll get to that. This is perfect. I have a minute and a half to just remind you of where we were. Okay, these are the things that we have seen. Okay, these are the equilibria. These are the stable things that you can make. Okay, when we start to change the laws of nature, we'll be interested in are the equilibria still there? Can I still make stars? And importantly, do I actually still make stars? Okay. Now we haven't really looked at that second question. Let me slightly skip ahead. Hang on, sorry. Actually, we're just about at the time to stop. Where is
Did you have something to finish on this?
no, let's stop with this plot.
Very good. Okay, thanks.
I think this is This is a good place to stop.